So this video accompanies the organizer on page, at this point, 419, which is about molecular polarity. So if you remember when we were learning about different types of bonds, we learned about bond polarity when we were taking a look at polar covalent bonds. And so a bond that's polar covalent results in what we called a bond dipole. And that's when the electron density is pulled more towards one atom than the other. So you have electronegativity values that are different enough that one atom pulls a little bit harder. If you remember, we showed that by showing that the atoms have partial charges. The less electronegative atom gets the partial positive, the more electronegative atom gets the partial negative. And then we can actually show the bond dipole by drawing an arrow where the tail looks like the plus because it's near the more, or the less electronegative atom. And then the arrow is pointed in the direction of the more electronegative atom because that's where the electron density is being pulled. It's concentrated more towards one atom than it is another. So that can lead into having polar molecules. It doesn't have to, but it can lead into polar molecules. So the rest of this video is about how to determine whether the whole molecule is polar or not just individual bonds. So a polar molecule is one which has a distinct positive end and a distinct negative end. So the whole molecule itself has electron density being pulled in one direction. Polar molecules are going to result in very different behaviors than nonpolar molecules. And so this is why we want to be able to predict polarity, because as we move on to types of or properties of polar molecules, we want to take a look at that. So there are a couple steps. As you can see on the organizer, there's a couple of steps that go into determining molecular polarity. Step one is asking yourself, is this an ionic compound or is this a molecular compound? How are you going to know? Well, if you remember, ionic compounds are going to have metals and nonmetals in them, whereas molecular compounds are just going to have nonmetals. So that's what you want to look for. What kinds of atoms are involved? If it's molecular, your work is done. You can automatically assume that the substance is polar. However, if it's molecular, you're going to have to do a little bit more work. So moving on to step two, there's quite a lot involved in doing step two. You've got to figure out you have to actually assign bond dipoles and then consider the shape of the molecule. So start off, you might have to draw the Lewis structure or at least the structural formula. Then you've got to determine the three-dimensional shape based on Vesper theory. And finally, you want to determine if there's any bond dipoles using electronegativity values. Once you have done that, you can conclude that if there are no bond dipoles, regardless of what the substance is and what the shape is, it is going to be nonpolar. However, if there are bond dipoles, then you have to go on to step three, because just because there's bond dipoles doesn't mean the whole molecule itself is going to be polar. So there's two ways that you can determine the polarity of the molecule. 3A is probably the easier of the two ways at this point, because 3B can be a little complicated, the idea of symmetry. So this idea is for you to take a look at the direction of the bond dipole arrows. If all the arrows are pointing in the same general direction, that means the electron density is being pulled in one direction. That means the molecule itself is going to be polar. If, however, you have arrows pointing in opposite directions, so like all the heads are pointing in or all the heads are pointing out, then the arrows essentially cancel each other out. The bond dipoles cancel each other out, and so you wind up with a nonpolar molecule. So once again, just because the atom is polar, just because the bonds are polar, doesn't mean the whole molecule itself is going to be polar. So if there's no direction of flow, you've got a nonpolar molecule. But if you can see that the electrons are definitely being pulled in one direction, you've got a polar molecule. The other way is to use the idea of symmetry. The problem is the molecule needs to be symmetrical in every way, not just left to right, but up, down, and all sorts of other ways. And there are different degrees of symmetry. You can have 120-degree angle symmetry and so forth. So this one's a little harder to do. But if you determine that there is symmetry in all directions, the molecule will be nonpolar. But if there is any asymmetry going on, chances are the molecule is going to be polar. Now, asymmetry doesn't necessarily mean polarity, because you also have to consider, are there bond dipoles? So remember that. So let's do a couple of examples. These, again, are the ones that are on your organizer. They're on the back side. So CAF2 is the first one. So step number 1, is it ionic? Is it molecular? You determine that it's ionic. So what's your result? Number 1, it's polar. You are done. No more thinking to do. Example number 2, taking a look at water. Step 1, we determine that it's molecular. We've got 2 non-metals here. So then step 2 requires you to draw the Lewis structure, figure out electronegativities, figure out bond dipoles. So everything leads into this idea. You have a bent molecule. Hydrogens have the more positive end. Their electronegativity is only 2.1. Oxygen has an electronegativity of 3.5. So the electrons are being pulled towards oxygen. Now, how do I use that to figure out if it is a polar molecule? Well, step 3 says, do I have a direction of flow? And in this case, everything's going up. So the result is that, yes, this is a polar molecule. So now, in terms of symmetry, yes, it's symmetrical from left to right, but it's not symmetrical from top to bottom. All the electron density is being pulled up towards oxygen. None of the electron density is being pulled down towards hydrogen. So it is a polar molecule. All right, third example, CO2. So step 1, non-metallic stuff, so you got a molecular substance. Step 2, hopefully you wind up noticing that it is a linear molecule. So even though oxygens are very electronegative compared to carbon, they are being pulled in opposite directions. So here you have an example of bond dipoles, but because the arrows are opposing each other, you have cancellation, and so your result would be a nonpolar molecule. Plus, this is a completely symmetrical molecule. Left to right, top to bottom, any way you look at it, it's very symmetrical. So your result has to be that it is nonpolar. Example number 4, we've got naphthalene, C10H8. Hopefully it's obvious to you that it is polar. Here's the structure. There's no way for you to know that quite yet, but there's the structure of naphthalene. So if you take a look at everything, carbon has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.1, which means the difference between that is only 0.4. There are no bond dipoles here. So even though this is a really complicated looking molecule, there are no bond dipoles. And here's a hint. Anytime you have just carbons and hydrogens, it's always going to be nonpolar because of the fact that the difference isn't big enough. So carbons and hydrogens mean we have organic materials. Anytime you have this kind of organic molecule with just carbons and hydrogens, nonpolar. So our result, nonpolar, because there are no bond dipoles. All right, so we've gone through a few examples. It is now your turn. So these are substances that are all listed on your assignment sheet along with the answers, not assignment sheet, organizer. So give these a shot. Pause the video. If you don't have the organizer with you, pause the video, try and figure these out. And then the next slide I will turn to momentarily has all the answers. So again, pause the video here, try all of these, And then now I'm flipping. You can take a look and see what your answers are. All right, so that's polarity. Good luck with all that practice. And then you've got some homework to do with it as well.